Right, this is simple harmonic motion for module 4.2. Now, simple harmonic motion borrows a lot of ideas from circular motion. I'm just going to call it SHM from now on. I hope you get mine, but I'm thoroughly lazy in that regard. Simple harmonic motion steals ideas from circular motion. Why does it do that? Well, they're both very similar in that they're periodic motions. They repeat themselves. Circular motion goes through one complete circle, that's a cycle, and then starts the same thing again. Simple harmonic motion does exactly the same. It has this cycle. That means we can borrow ideas of frequency, of time period, and of angular frequency from circular motion. Now, the angular frequency is the one that is least intuitive, because you won't necessarily see something in simple harmonic motion moving through an angle. We're not talking about a literal angular velocity there. We're talking about something with a cycle length of 2 pi radians, and we're just choosing to use that as a measure of our cycle. We're saying each cycle lasts for 2 pi radians. And so half cycle is pi radians. And we can start to link back to module 2 ideas of waves of phase and phase difference, and all of that becomes very useful. So angular velocity is there just to help us to understand this periodic motion, simple harmonic motion. Now, we define SHM. It is defined by 2 characteristics. It is a motion, it's a repetitive motion, it's an oscillation in which the acceleration is proportional to and opposite to the displacement in the equilibrium position. So A, the acceleration has to be proportional to minus x, the displacement in equilibrium. That is your defining condition for SHM. If neither of those things are true, it is not SHM. So, that's our definition. Now, what does this look like? Now, from Matt's point of view, that's quite an interesting equation, because acceleration is actually mathematically d2x by dt squared. It's the second differential of displacement with respect to time. And so what you've got here is you're saying that this second differential of x with respect to time is equal to minus some constant times x. Now that's very interesting because x is related to the second differential of itself. That means there must be some specific solutions to that kind of problem, and there are, and they always come in the same form. Now for now, we're going to use a function, A level, we're going to use this function to describe the solution for this equation, and it is this. X equals A cos of 2 pi ft. Now, if you're not a mathematician, just accept that this is a solution of that equation. If you are a mathematician, feel free to go and look into it and find out why it is and how it works. For the moment, we'll use this equation to describe SHM. Now, this is quite a simple equation. It's got 2 variables, x and t, and x depends on t. Now, 2 pi f, 2 pi is constant, f is just the frequency of this system. So I hang a mass on spring, it will oscillate 10 times a second, it has a frequency of 10 Hz. So I can just stick that number in there. It will be a constant for the system. This cos function allows for the periodic nature. It means I go from a maximum to a minimum and oscillate through in a wave-like fashion. This A sets the amplitude. It is the maximum displacement from equilibrium. So the maximum value of this cos function is 1. So at that value, my displacement is equal to A, the amplitude, and obviously cos is to minus 1 as well, and so there I have a negative amplitude of x minus A. But that is the basic equation that will describe simple harmonic motion. From that, if I were to differentiate it twice, I'd end up with an expression for acceleration that is equal to minus 2 pi f whole squared times x. Again, if you're a mathematician, you'll probably be able to see if I differentiate cos, I get a minus sign. If I differentiate that minus sign function, I'll end up with a minus cos function, which is where I get the x from, because it's exactly the same as that. And each time I differentiate it, I take out a factor of 2 pi f, which becomes the coefficient in front. But this satisfies our condition that A is proportional to minus the displacement, A is proportional to minus the displacement, and it has this constant proportionality of minus 2 pi f. This means I have a maximum acceleration of minus 2 pi f all squared a, which is also given to you on the problem sheet. So that's a maximum acceleration, but in reality the acceleration will vary depending on its position, and it will have zero acceleration when it's in equilibrium. Now, in reality, if you were doing a maths degree or doing a physics degree where you are using a little bit more maths, you would come up with an expression for velocity. It's just the first differential in this, and it would be velocity would be equal to minus 2 pi f a sine 2 pi f t. But we're not going to use that because it's not in the syllabus, because it's not allowing to calculate it. But they have managed to derive another expression for velocity. And this velocity expression is that the velocity at any given moment will be v equals plus or minus 2 pi f times the root of a squared minus x squared. Now, if you want to, you can just use that equation. It will of course give you a maximum speed equal to plus or minus 2 pi f a. Will be when it is at equilibrium, not at the fastest. Now, that is usable as is. If you're interested in where it comes from a consideration of energy in the system. So if I look at a pendulum, which is one of the two classic examples. So here is a pendulum. And as that pendulum swings, we'll mark its equilibrium line here. So this is its equilibrium position there. And this is its maximum amplitude in one direction, and this is its maximum amplitude in the other. Now, as that pendulum swings, it swings from a point where it has zero kinetic energy, because it's stationary, and it has maximum potential energy. And it swings from equilibrium where it has maximum kinetic energy, because it's moving at its fastest, but it has zero potential energy, and it swings out to the opposite side where it has maximum potential energy and zero kinetic energy. So you have this cycle of kinetic energy and potential energies being exchanged. Now, if there is no damping and no energy is lost from the system, then this equation holds. Basically, it's derived from the mass spring system in Pittsburgh. So the other classic example is to have a spring and attached to the bottom of the spring to have some kind of mass. And if I displace this mass from equilibrium, so I pull it down, it will then oscillate and bounce back up and will be on equilibrium. Now, this equation is derived from looking at the potential energy stored in spring in terms of x squared displacement from equilibrium, and then taking the difference between the maximum potential energy, which is related to a squared, maximum displacement, taking away the actual potential energy, which is related to x squared, and assuming that all of that difference between maximum potential and the actual potential is kinetic energy, assuming that no energy is lost in the system. And you stick that into half mv squared rearrange for v, and that's where this equation comes from. You don't need to be able to derive it. That's its origins. Now here we have our two classic examples. There are other things that will oscillate with SHM, but the pendulum and the mass on spring are the two classic examples. Now, by looking at this standard equation, you can then derive what the time periods will depend on for these two examples. And it turns out that for a pendulum, the time period is equal to 2 pi times the root of L over Q. So that's interestingly and somewhat counterintuitively tells you that the time period of the pendulum only depends on its length and the gravitational field strength of the Now, in practical terms on Earth, that means that the only way to change the time period of the pendulum is to change its length. Obviously, it would change move from one to another amplitude, but time period depends primarily on that. Now, that is counterintuitive, but it means that mass has no effect at all. My favourite exam question in this topic looks at Big Ben. The clock in the tower that also houses Big Ben has a very long pendulum, and they change the pendulum if it is not keeping time by putting a coin on a pile of coins at the bottom of the pendulum. And a lot of people will instinctively think that that changes the mass and this changes the time period. But in reality, what it's doing is changing the effective length of the pendulum by ever so slightly raising the centre of mass. But body of the pendulum. So very, very careful. A pendulum does not have a time period dependent on minutes. A spring mass system, however, does. Its time period is equal to 2 pi root m over 4. K is the spring constant that you get from Hooke's law measure 2, and mass is the mass of the pounds on the spring. So here we only have 2 ways of changing the time period of a mass spring system. If you keep the same spring, then the only thing you can do is change the mass. Obviously the frequencies are just the inverse of these functions, so you can work out the frequency of these systems as well. And that frequency becomes really important when you look at resonance. Resonance is an effect whereby if you affect an oscillating system with a driving force at its natural frequency, the frequency it wants to vibrate at, which we'll sometimes call F naught. If you hit it with a frequency force at frequency of F naught, you will get massive oscillations. Those oscillations can be dangerous. There have been bridges fall down, buildings collapse, wine glasses shattered by voices, because when a body is hit at its natural frequency, the amplitude increases massively. You need to be able to describe what would happen if you had a driving frequency starting at 0 but gradually increased frequency up to and beyond the natural frequency. And that's a useful and nice question for the look at. This is one of the areas where you actually work qualitatively as well as numerically. The final idea to have in your mind is that of damping. Now damping basically means adding a resistive force to one of these situations. That resistive force will always act in the opposite direction to velocity, because it's quite slow down, and it will remove energy from the system, which means that these equations no longer valid, because effectively the amplitude is changed. You're gradually decreasing the amplitude by removing energy from the system. Damping can be shown to follow an exponential effect. So similar to the equations we've used to simulate classicals, if you can measure the amplitude of the successive oscillations, there should be an exponential nature to look for those oscillations.